Our next speaker continues a series of people I've been investigated with and had great results with what they've done. This is Dr. Eddie Wang, who is from Kevin McElway's and Jerry Shapiro's group in British Columbia. He's now working with Dr. Cristiano's group in Colombia, and he will be talking about DNA methylation profile of monozygotic and dizygotic twins discordant for alopecia areata.
Alright, thank you for the introduction. Yes, like Dr. King said, I used to work with Kevin to identify autoantigen epitopes in AA. And now I am studying with Angela Cristiano for looking at epigenetics of alopecia areata. So as you may have heard from many of the talks these past couple of days, AA is one of the most common autoimmune diseases in the US with about 1.7% lifetime risk. However, in the twin study for AA, there's only about 55% concordance rate. And this phenomenon is also observed in other autoimmune diseases, such that there's a missing heritability observed in the GWAS study, and you cannot explain that there's only about 40% concordance rate in the Taiwan diabetes in monozygotic twins. And one of the hypotheses that to explain this observation is that there could be some sort the AA susceptibility could be affected by the various epigenetic mechanisms. So today I'll be talking to sharing two different stories with you, both on epigenetics. And the first one is about we take advantage of the twin samples that we have for humans, and I look at the DNA methylation profile of monozygotic and dizygotic twins, both discordant for AA. And this is an example of a transcriptional regulation. And then I'll talk about the identification of microRNA expression in the C3H mouse model of AA, and this is an example of a translational regulation. So with the human samples, we have performed a 450K methylation array, and on 6 pairs of monozygotic and 4 pairs of dizygotic twins. And immediately on the top, you can see that there is very different methylation level in between different dizygotic twin pairs, and also within between different individuals as well. Whereas if you look at the monozygotic twins, they are actually very similar. There are certain genes that share very similar methylation profile between pairs and also between individuals, even though one has A and the other one does not. But the genes that are most interest to us are the ones in the middle here, where it shows a different methylation level between the sibling that has A compared to the normal hair sibling. And these genes are likely to be the ones that could play a role contributing to the different inter-individual susceptibility to AA. So to take a step back and look at things globally, the global methylation level between the AA and the non-AA siblings are actually very similar. And this is actually same for both monozygotic and dizygotic twins. However, if you look at individual methylation sites, there was actually a higher number of hypermethylated sites in the AA sibling compared to the no-AA. So this could potentially mean that there is an indication that there is a higher number of gene suppression happening in the AA siblings. So with the genes that we infer from these differentially methylated sites, we try to determine the common biological processes that in the monozygotic twins, and we found that enrichment of the genes that fall within the process for limb morphogenesis, antigen presentation, and also cell adhesion. And for the disease pathway analysis, the genes for process for antigen presentation also come out as one of the important ones. For us, we are really interested in genes such as collagen 13 and HLA-DRB1, mainly because collagen 13 has been indicated in cardiac dysfunction and also in Graves' disease, while HLA-DRB1 has been found in our previous independent GWAS study, where the SNP, the SNP, is actually an eQTL site for the HLA-DRB1. And this could, of course, affect its expression and maybe even different antigen presentation. So to conclude the first part of the talk, I I have found different methylation profile between monozygotic and dizygotic twins. And this information has helped me to identify a panel of genes that were differentially methylated. But of course, a lot of validation is still going on in the lab right now. But by utilizing both genetic and epigenetic analysis, we were able to confirm and reveal additional genes, risk genes, that could be important for age susceptibility. And the example here is collagen 13 HRD1, and they are involved in other diseases such as rheumatoid arthritis and Graves' disease. So moving on to the mouse stuff, I have performed mouse microarray profiling in the skin of the mice that have developed AIDS spontaneously compared to the unaffected mice. And so in here, I'm showing you that just a very brief description of what microRNA is. The microRNA inhibition is a mechanism where the mRNA gene target is degraded after they were bound to the complementary short RNA sequence. So this will result in reduced of translation in general. So we performed a microRNA expression array on the lesional skin and the control skin, and it revealed abundant amount of differentially expressed microRNAs. And I'm just showing you a little part of the result that we have here that show a significant decrease of several microRNAs in the skin of AA mice compared to the unaffected. And these genes I'm showing you these genes because they are also involving they also targeting very interesting genes that is involving antigen presentation and also interferon response. And what I would expect is that the expression of genes will be inversely correlated with the expression of microRNAs. But first, to put things in the bigger picture, we have seen a lower level of microRNA in the AA mice targeting things like TAP2, and which may lead to eventually to higher expression of TAP2 protein itself and lead to higher antigen presentation. And conversely, we have a higher expression of microRNA 155 in the skin of AA mice. This may reduce the CTLA-4 induced apoptosis of T cells, leading to the disease. In addition, there were also lower amount of multiple microRNAs that were targeting STAT1 and also BAC1, and these may accentuate interferon signaling and very so similar to what we have seen before in the AA mice. So to validate the actual gene expression of these target genes, we have also performed qPCR and microarrays on some of these gene targets, and they will actually just confirm what I was suspect earlier. The gene targets were actually upregulated when the microRNA was downregulated. So in summary, there is a differential expression of microRNA in the mice with spontaneous AA. And these could potentially lead to new ways of treating AAs, like what we seen earlier talk this morning, by maybe using mimic RNAs, microRNAs. And so, as an overall summary, I provide examples that may explain the missing heritability that was observed in G1 study and identify genes that could potentially be risked with epigenetic modulation. And something interesting is that with increasing studies on epigenetic mechanisms, there are right now new drugs coming out, and one of these are shaped from tetralogate that is a histone acetylase inhibitor, and it's actually going to clinical trial phase 2 a few years ago. So with that, I'd like to thank my supervisor, Dr. Cristiano, and my lab member, and also Ben Tycho's lab for their support, help, and also NAP for their funding support. Thank you.